In a general sense, linear equations belong to elementary algebra. They are defined within a formal symbolic framework. The framework is abstract and internally consistent. A linear equation is a specific type of equation. It follows a restricted structural form. The form is defined by linearity. Linearity refers to the absence of higher degree terms. Only first-degree expressions are permitted. This restriction is assumed throughout the discussion. A linear equation contains variables and constants. Their roles remain unchanged from earlier definitions. The equation relates these symbols through equality. The equality expresses a formal condition. It can be observed that the structure is simple. Simplicity here refers to symbolic form. It does not imply ease or difficulty. The form is predictable and repetitive. Predictability is a defining feature. One may think of linear equations as structurally uniform. The uniformity reduces variation. Reduced variation supports formal analysis. The equation is written as a symbolic statement. The statement does not imply action, it merely asserts a relation. This relation is linear in nature. Linearity is defined formally, not intuitively. The definition relies on symbolic constraints. Variables appear without exponents beyond the first degree. Constants appear as fixed quantities. No additional symbolic complexity is introduced. The equation remains within defined limits. These limits are part of the formal system. They are not negotiated or adjusted. We may restate this description calmly. A linear equation is an equation with restricted structure. The restriction applies to how variables appear. Only linear appearances are allowed. This allowance defines the category. The category exists within algebraic classification. Classification serves organizational purposes. It does not alter the equation itself. The equation remains unchanged by classification. It can be observed that linear equations are stable forms. They do not vary in type once defined. Their structure is consistent across instances. Consistency supports repetition. Repetition supports monotony. We may remain with this description quietly. The linear equation exists as a formal object. It does not depend on interpretation. It does not require application. The language describing it remains neutral. Sentences proceed slowly and evenly. No emphasis is introduced. No conclusion is suggested. The definition stands without resolution. We may now consider the process of symbolic transformation. This process is applied to linear equations in algebra. The application is formal and rule-governed. No interpretation is required during transformation. The equation is treated as a symbolic object. Transformation refers to changes in symbolic form. These changes do not alter the underlying relation. It can be observed that equality must be preserved. Preservation is assumed throughout the process. The equation before and after transformation remains equivalent. Equivalence is a formal condition. It does not rely on meaning or context. One may think of transformation as rearrangement. The rearrangement follows accepted algebraic rules. The rules are stable and repetitive. Repetition supports predictability. Predictability supports monotony. The goal of transformation is symbolic isolation. Isolation refers to separating the variable symbol. The separation is formal and gradual. No step introduces conceptual novelty. Each step resembles the previous step. This resemblance reduces variation. The variable remains unchanged in identity. Only its position within the equation changes. The constant symbols also remain unchanged. They may be repositioned symbolically. The repositioning follows equivalence-preserving rules. These rules are not questioned here. They are accepted as part of algebraic structure. We may restate this description using similar phrasing. Symbolic transformation alters form without altering relation. The alteration is controlled and deliberate. No symbolic operation is arbitrary. Each operation is permitted by convention. Convention governs algebraic manipulation. The conventions are shared and stable. Stability underlies the entire process. The process proceeds without urgency. No emphasis is placed on outcome. Outcome is not required at this stage. The act of transformation is sufficient. One may think of the equation as gradually reordered. The reordering maintains balance. Balance is expressed through equality. Equality remains constant throughout transformation. The equality symbol retains its meaning. Meaning does not shift during manipulation. The process remains abstract and unemotional. Sentences describing it remain even and repetitive. We may continue to remain within this explanation. Symbolic isolation is achieved through repeated rearrangement. Rearrangement does not change symbolic identity. It only changes symbolic placement. Placement within the equation is not essential. The relation expressed remains unchanged. This unchanged relation defines equivalence. Equivalence preserving operations. The tone remains neutral and academically restrained. Equivalence preserving operations are applied to linear equations. These operations do not change the solution set. The solution set remains implicit and unexamined. The equation is treated as a formal symbolic statement. Operations act on symbols rather than meanings. It can be observed that equality must be maintained. Maintenance of equality is assumed at every step. The operations are defined within algebraic convention. Convention determines which actions are permitted. Permitted actions follow established symbolic rules. These rules are consistent and repetitive. Repetition reduces variation within the process. Reduced variation supports monotony. One may think of operations as formal adjustments. The adjustments alter symbolic appearance. They do not alter symbolic validity. Validity is preserved through equivalence. Equivalence means sameness of relational meaning. This meaning is formal and abstract. It does not depend on interpretation. Operations may be applied to both sides equally. This equal application preserves balance. Balance is expressed through the equality symbol. The symbol remains unchanged throughout operations. Its function remains stable. The equation before operation and after operation remains equivalent. This equivalence is assumed rather than demonstrated. Demonstration is not required here. The process is accepted as standard practice. We may restate this description in similar language. Equivalence preserving operations change form, not relation. The relation is defined by equality. Equality is maintained by symmetric application. Symmetry is a formal requirement. It ensures stability of the equation. Stability supports predictable structure. Predictable structure supports passive engagement. Operations are applied sequentially. Each operation resembles the previous operation. This resemblance reduces novelty. The lack of novelty is intentional. The equation gradually changes appearance. Its internal balance remains unchanged. The symbols retain their identities. Variables remain variables throughout operations. Constants remain constants throughout operations. No symbol changes category. Category stability is assumed. The operations respect these categories. Respect here means formal compliance. No emotional or intuitive meaning is attached. The process remains abstract. It proceeds without urgency. No final state is required at this moment. The act of operating is sufficient. We may continue to remain within this explanation. Equivalence preserving operations maintain formal sameness. Sameness is central to algebraic manipulation. This centrality is assumed quietly. No emphasis is placed on importance. Abstract notion of solution sets. A solution set is associated with a linear equation. The association is formal and symbolic. The solution set consists of values that satisfy equality. Satisfaction here is a formal condition. It does not involve interpretation or intuition. The equation defines a condition of equality. The solution set is defined relative to this condition. It can be observed that the set may contain elements. The elements are values assigned to variables. The assignment is symbolic and abstract. No concrete meaning is required. One may think of the solution set as a collection. The collection exists within algebraic structure. It does not depend on representation. Representation does not alter the set itself. The solution set may be empty. The emptiness is a formal possibility. It does not require explanation. The solution set may also contain a single element. This containment is symbolic. It follows from the structure of the equation. Multiple elements may also be included. In linear equations, the structure limits this possibility. The limitation is part of classification. Classification is descriptive, not prescriptive. The equation determines the solution set. The determination is implicit. It is not emphasized. We may restate this description slowly. A solution set contains all values satisfying an equation. The satisfaction is defined by equality. Equality remains the central relation. The equality symbol retains its role. The solution set does not alter the equation. It is derived conceptually. The derivation is abstract. It doesn't require procedural focus. Focus remains on structure. The structure of a linear equation is simple. Simplicity here is formal. It does not imply effort or ease. The solution set reflects this structure. Reflection is symbolic, not visual. One may think of the solution set as stable. Once defined, it doesn't change. Change would require a different equation. The equation remains fixed. The solution set corresponds accordingly. This correspondence is formal and consistent. Consistency underlies algebraic reasoning. The reasoning proceeds without urgency. No emphasis is introduced. The language remains flat and repetitive. We may continue to restate these relations. Linear equations define conditions. Conditions determine solution sets. The determination is abstract. It does not depend on interpretation. The solution set exists as a concept. The concept is part of algebraic language. It does not require visualization.